Good morning. Today we have to see about diffraction of light. Diffraction of light. Today we have to see about diffraction of light. See. Suppose this one as source of light. Suppose this one as source of light, and suppose this one as obstacle. Then incident rays from source S bends near the edge of an obstacle like this. The phenomenon of bending of light waves. The phenomenon of bending of light waves near the edge of an obstacle and spreading out a geometrical shadow. याची इथे एक अशी shadow तयार होत असते. And spreading out a geometrical shadow is called as diffraction of light. The phenomenon of bending of light near edge of an obstacle. The phenomenon of bending of light near edge of an obstacle and produces a geometrical shadow. The phenomenon of bending of light near the edge of an obstacle and produces a geometrical shadow is called as diffraction of light. Light actually travels along a straight line only. Light actually does not bend around edge of an obstacle but produces a shadow due to emission of secondary waves. Actual light travels only along straight line, but at the edge of obstacle secondary waves produces, and this secondary waves produces a geometrical shadow. This phenomena is called as diffraction of light. What is diffraction of light? The phenomenon of bending of light near edge of an obstacle and produces a geometrical shadow is called as diffraction of light. Actually, light does not bend at the edge of obstacle but produces a secondary waves. Produces a geometrical shadow due to emission of secondary wavelets on the edge of obstacle. Okay. Now, types of diffractions. Types of diffractions. There are mainly two types of diffraction. One Fresnel, F-R-E-S-N-E-L, Fresnel diffraction, and one more that is Francoeur diffraction, F-R-O-U-N-H-O-F-E-R, Francoeur diffraction. Types of diffractions: Fresnel diffraction and Francoeur diffraction. If source of light is at finite distance, then both incident wavefront as well as diffracted wavefronts are either spherical or cylindrical. When source of light is at finite distance, then incident wavefront is either spherical or cylindrical. hence light after diffraction converge at a point on screen. See here, if source of light is at finite distance, suppose this one as obstacle, this one as source of light. If source of light is at finite distance, then incident wave front is either spherical or cylindrical. And hence, after diffraction, light converge at a point on screen and no converging lens is necessary. No converging lens is necessary to observe it. Such a type of diffraction is called as frictional diffraction. See once more, types of diffraction. Frictional diffraction. If source of light is at finite distance, then incident wavefront is either spherical or cylindrical, and hence after diffraction light converge at a point on screen, and hence no converging lens is necessary to observe it. Such a diffraction is called as frictional diffraction. Transfer diffraction. If source of light is at infinite distance, then incident wavefront is plane. If source of light is at infinite distance, if source of light is at infinite distance, then incident wavefront is plane, and hence diffracted wavefront is also plane. Both incident wavefront as well as diffracted wavefront are plane, and hence converging lens is necessary to converge light after diffraction. Means in this case converging lens is necessary to converge light after diffraction. Such a type of diffraction is called as transfer diffraction. If source of light is at infinite distance, then both incident wavefront as well as diffracted wavefront are plane, and hence converging lens is necessary to converge diffracted light on screen. Such a type of diffraction is called as transfer diffraction. What is diffraction of light? The phenomenon of bending of light near edge of an obstacle and produces a geometrical shadow is called as diffraction of light. There are two types of diffractions, that are frictional diffraction and transfer diffraction. Frictional diffraction: if source of light is at finite distance, then incident wavefront is either spherical or cylindrical, and hence after diffraction light converge at a point on screen and no converging lens is necessary to observe it. Such a type of diffraction is called as frictional diffraction. In case of transfer diffraction, source of light is at infinite distance. And hence both incident wavefront as well as diffracted wavefronts are plane. Therefore, converging lens is necessary to converge light on screen to observe diffraction. Such a type of diffraction is called as transfer diffraction. Okay. मग ह्या दोघातला डिस्टिंग्विश फ्रेशनल डिफ्रॅक्शन FRESNEL फ्रेशनल डिफ्रॅक्शन ट्रान्सफर FROUNHOFFR ट्रान्सफर डिफ्रॅक्शन. First, source of light is at finite distance. Source of light is at infinite distance. Second one, incident wavefront is spherical or cylindrical. Incident wavefront is plane. Third one, no converging lens is necessary to observe diffraction pattern. Here converging lens is necessary to observe diffraction of light. These are two types of diffraction. Okay. Now diffraction at single slit. Now diffraction at a single slit. Diffraction at a single slit like this. One more important point. Diffraction at a single slit. See. Diffraction at a single slit. Suppose this one as a screen like this. This one as incident wavefront. Okay. These are incident rays or plane incident wavefront. Suppose this one as a plane incident wavefront. Diagram. See here. Consider a parallel beam of monochromatic light. Consider a parallel beam of monochromatic light. Normally incident on a narrow slit AB. Consider a parallel beam of monochromatic light of wavelength lambda normally incident on slit AB of width A. Width of slit A. Suppose diffracted light is focused by convex lens L on screen. Suppose that diffracted light is focused on screen by convex lens L, which is kept at focal plane of lens. This is focal plane. This is focal plane or focal length फार माने ठिकाणी. This is converging lens. This lens is kept or this screen is kept at focal plane of convex lens. See once more. Consider a parallel beam of monochromatic light of wavelength lambda normally incident on slit AB of width A. Suppose that diffracted light is focused on screen by a converging lens L, which is kept at focal plane of lens. Consider a parallel beam of monochromatic light of wavelength lambda is incident normally upon narrow slit AB of width A. Suppose that diffracted light is focused by a convex lens L on screen, which is kept at focal plane of lens. Now, see. Now see. Position of central maxima. Position of central maxima. First position of central maxima. Let O be the center of slit and P naught be the center of screen. Let O be the center of slit, P naught be the center of screen. Then path difference between waves arriving from A and B and reaches at P naught is 0, as well as path difference between rays in upper half and corresponding point in lower half and reaching at P naught is 0, and hence resultant intensity at P naught is maximum and corresponding point is bright, called as position of central maxima. See once more. Let O be the center of screen, P naught be center of slit. Let A center of slit, P naught be the center of screen. Then path difference. समजा हिथून जाणारा हा रे हिथून हिथं या डायरेक्शनला, हा रेज हिथून हिथं या डायरेक्शनला, मग हा पाथ आणि हा पाथ या दोघातला पाथ डिफरन्स. Waves arriving from A and B and reaches at P naught. अर्थात हे डिस्टन्स आणि हे डिस्टन्स इक्वल आहे, त्यामुळे त्यांच्यातला पाथ डिफरन्स 0 असतो. Let A be the center of slit, P0 be the center of screen. Then path difference between waves arriving from A and B and reaches at P0 is 0. Also, path difference between each point in upper half and corresponding point is lower half and reach at P0 is 0, and hence point P0 is of maximum intensity called as position of central maxima. Now, position of first minima. Position of first minima. Let P be any point at on screen at angular position theta. Suppose this one as angular displacement theta. हा अँगल थीटा असेल तर हा पण अँगल थीटाच, हा पण अँगल या ठिकाणचा थीटा. लेट पी बी एनी पॉइंट ऑन स्क्रीन at angular position theta as AC is perpendicular to B, as AC is normal to AM, as AC is normal to AM. Path difference between waves from A and B and reaching at P is BC. See here once more. Let P be a point on screen at angular separation theta. Let AC perpendicular to BC. Draw AC perpendicular on BC. Then path difference between waves arriving from A and B and reaches at P0 is BC. That is path difference is equal to BC. This BC is nothing but A sin theta, or path difference is equal to, इथं sin theta चा फॉर्म्युला वापरतो आपण. sin theta is equal to BC divided by AB, means BC is equal to A sin theta. Path difference BC is equal to A sin theta, which is equal to suppose lambda. Therefore A sin theta is equal to suppose wavelength lambda. This path difference is suppose lambda. Let K be a point. Let K is a point at midway between A and C. Then OC, then OK, then OK is equal to A by 2 sin theta, or 1/2 BC. See once more. Position of first minima. Let P be a point on screen having angular separation theta. Draw AC perpendicular to BC. Then path difference between waves arriving from A and P and reaches at P is equal to BC. या दोघातला path difference BC means path difference is equal to BC. Suppose this path difference is lambda. From this triangle BC is equal to A sin theta. Therefore, A sin theta is equal to lambda. Suppose this is equation number 1. Let K is midpoint of AC, then OK is equal to 1/2 BC. BC चा half OK येईल, which is equal to lambda by 2. Thus path difference between AP and OP is lambda by 2. AP and OP is lambda by 2. As a result, these two waves produces destructive interference at P, and therefore destructive interference produces at P, and point P is of minimum intensity, called as position of first minima. Okay. This discussion can be extended to points on screen having path difference 2 lambda. आता हेच डिस्कशन जर आपण पुढच्या पॉइंटला घेतलं, having path difference 2 lambda, 3 lambda, 4 lambda like this, then first at the location of nth minima, at location of nth minima, at the location of nth minima, path difference between extreme rays A sin theta is equal to plus minus n lambda. If we assume the maxima in between, if we assume maxima in between these minima, then location of nth maxima, if maxima is lies between two minimas, then path difference between extreme two rays, that is A sin theta is equal to 2n minus 1 lambda by 2. In this way, diffraction of light can be explained at single slit. Okay. Now one more point, Rayleigh's criterion. Rayleigh's Rayleigh's criterion हा एक आपल्यासाठी पॉइंट आहे अबाउट Rayleigh's criterion. The ability of an optical instrument, the ability of an optical instrument, the ability of an optical instrument to distinguish two objects separated from each other. Two objects separates is called as resolving power of that optical instrument. The first of which about resolving power of an optical instrument. The ability of an optical instrument to distinguish two physically separated objects as two distinct objects. The ability of an optical instrument to distinguish two physically separated objects as two distinct objects is called as the resolving power of optical instrument. This resolving power depends on the aperture, aperture, that is diameter of lens. Diameter of lens, and one more, that is wavelength of wave. Resolving power of optical instrument depends upon diameter of lens, that is aperture, and wavelength of light used. The minimum visual angle. The minimum visual angle, the angle subtended at eye by two objects to be resolved between two objects that can be resolved by instrument is called as limit of resolution. Limit of resolution. What is limit of resolution? What is limit of resolution? The minimum visual angle. Suppose these are two objects. Suppose this one as optical instrument. Then minimum visual angle. Suppose this one as angle theta. The minimum visual angle, that is angle subtended at eye by two objects to be resolved, that can be resolved by instrument is called as limit of resolution of that instrument. What is limit of resolution? The minimum angle. The minimum angle subtended at eye by two subjects, two objects to be resolved. Suppose this one as one object, this one as one another object. If these two objects are resolved from each other, then angle made by these two objects at eye is called as limit of resolution. The reciprocal of limit of resolution 1 divided by limit of resolution. The reciprocal of limit of resolution is called as resolving power. खरं तर इथं आपण डेफिनेशन केलेलीच आहे. तुम्ही काय करायचं, ही डेफिनेशन लक्षात ठेवायची. व्हॉट इज रिझॉल्विंग पॉवर? द ॲबिलिटी ऑफ अन ऑप्टिकल इंस्ट्रुमेंट टू डिस्टिंग्विश two objects separates from each other is called as the resolving power of that optical instrument. This resolving power depends upon the aperture, that is diameter of lens, and wavelength of wave. Now limit of resolution. The angle, the minimum angle फार ठिकाणी subtended at eye by two objects. The minimum angle subtended at eye by two objects to be resolved is called as limit of resolution of that instrument, and the reciprocal of limit of resolution is called as resolving power of that instrument. According to Rarish, two objects are just resolved. According to Rarish, suppose this one as one object. According to this Lord Rarish, two objects are just said to be resolved when minimum of diffraction pattern of one source is at maximum of is coincide central maxima of other source. समजा हा फर्स्ट सोर्स S1 हा सोर्स S2, पहिल्या सोर्सचा मिनिमा हा दुसऱ्या सोर्सच्या सेंट्रल मॅक्सिमावरती कोइन्साइड होत असेल. पहिल्या सोर्सचा मिनिमा हा दुसऱ्या सोर्सच्या सेंट्रल मॅक्सिमावरती कोइन्साइड होत असेल, किंवा पहिल्या सोर्सचा सेंट्रल मॅक्सिमा पहिल्या सोर्सचा सेंट्रल मॅक्सिमा इज कोइन्साइड विथ central maxima of second source. Then objects are said to be resolved. Just resolved. According to Rayleigh, two objects are just resolved when first minima of diffraction pattern of one source coincides central maxima of diffraction pattern of other, and vice versa. पहिल्याचा फर्स्ट मिनिमा. According to Rayleigh, central minima of first object is coincide with first minima of अदर सोर्स. पहिल्याचा सेंट्रल मॅक्सिमा आणि दुसऱ्याचा फर्स्ट मिनिमा हे जर एकाच ठिकाणी कोइन्साइड होत असेल, देन ऑब्जेक्ट्स आर सेड टू बी जस्ट रिझॉल्व्ड. अकॉर्डिंग टू रॅलिश, two objects are said to be just resolved if central maxima of first object is coincide with first minima of second, and vice versa. पहिल्याचा सेंट्रल मॅक्सिमा हा दुसऱ्याच्या फर्स्ट मिनिमवरती कोइन्साइड होत असेल, देन ऑब्जेक्ट्स आर सेड टू बी जस्ट रिझॉल्व्ड. The angular separation of first principle. The angular separation of first principle is d theta is equal to lambda divided by a. This is angular separation, and therefore limit of resolution is called as limit of resolution. The minimum separation between two linear objects that are just resolved at distance t from instrument. Suppose this one as a distance d. Suppose this one as a distance d. A, that is distance between these two sources. Then d theta can be written as d into lambda divided by a. Using this formula, limit of resolution can be determined. Okay, तर इथपर्यंतचा भाग आपल्याला टोटल आहे. हा झाला आपला वेव्ह ऑप्टिक्स 7th टॉपिक. राहिला जो पुढचा भाग आहे तो रिझॉल्विंग पॉवर ऑफ मायक्रोस्कोप अँड रिझॉल्विंग पॉवर ऑफ टेलिस्कोप आपल्या सिलेबस मधून तो डिलीट झालेला आहे. त्याचबरोबर पोलरायझेशन ऑफ लाईट हा पण पूर्णपणे भाग आपल्या सिलेबस मधून डिलीट झालेला आहे, आणि रिफ्रॅक्शन ऑफ लाईट ऍट प्लेन बाउंड्री. ओके.